So for this video, we're going to be talking about basics about functions in their graph. So we're going to be talking about, can you tell if it's a function when given a set of ordered pairs? What about if you're given some graphs or some equations? All right, and then just talking about function notation and finding some information as we evaluate functions and their graphs. So let's go ahead and get started here. So first off, real quickly here, definition of a relation just says a relation is any set of ordered pairs. So a lot of times in math, especially pertaining to graphs and different things like that, we're always talking about a set of ordered pairs that could give us, it could be points on a graph, it could be, just information, but really a relation is anything that you can make a comparison out of that you can put into ordered pairs. In this example, we have a number here and a dollar value here. It could be, a name and your height, a name and a student ID number. It could be, your favorite food in comparison to your favorite book. But really, a relation is just a comparison of two things. So when it comes to math, we deal with a lot of relations. And what we want really is a lot of times we want to figure out, is that relation a function or not? So that's kind of the main topic of this video here. So first off, book definition of a function is a correspondence from a first set, the domain, to a second set, the range, such that each element in the domain corresponds to exactly one element in the range. So to break this down just a little bit to show you what a function is and what a function is not. Right, if I input a value, let's say into an equation, if I plug in 2 into an equation, right, if it is a function if I get a unique solution for y. So let me give you a non-example here. So the example I have written here is talking about you work a job and you make $10 an hour at your job, right? So if that is so, if you work 5 hours, you are expected to make $50 that week, right? If you work 10 hours one week, you'll get $100. You work 15 hours one week, make $150. And then the next week you work 15 hours, but you only get 110. Right? If that situation were to happen, you would automatically go talk to your boss or see what's going on, because if you make $10 an hour and work 15 hours, you should get 150. It doesn't make sense that one week you make 150 and then the next week they only give you 110. There's something wrong with this equation, right? It's mathematically not making sense. There is an error there. This is an example of something that is not a function, right? It's not working out. And if we take a look at this, if we plug in 15 into this function, if we work 15 hours, this example gives us two different y values for it, right? So for the same input, we're getting two different outputs. So that's what this definition here is saying. It's saying if that happens, it is not a function. You should be able to plug in one value, get a unique solution for it, right? Just like, 5, 50, 10, 100, 15, 150. That part is okay. It's this one over here that throws it off. So in the next few examples, we're just going to take a look at a given situation and figure out, is it a function, yes or no? And then for most of them, we're going to go a step further and we're going to talk about what their domain and range is. Now, keep in mind, the domain, kind of think about it, it's the span of all the x values. So domain references to the x values for a function, whereas the range is the span of all of y values for that function. So in a nutshell, when you're given ordered pairs, to be able to tell if it is a function or not, if your x value repeats, it is not a function. If your x values are all unique, then it is a function. So if we take a look at example A, you want to focus on your x values. You have a 1, a 2, a 3, and a 4. Those are all unique. Those are all different. So yes, this is a function. If we go a step further to list the domain and the range, again, the domain and the range is, well, the domain is the span of our x values. So our x values are a 1, a 2, a 3, and a 4. Our range, so we're looking at our y values here. So a 6, we have another 6, we do not repeat values, and then we have a 10 here. So our range is just a 6 and a 10, no repetitions. Next example, again, let's answer our question, is the relation a function or not? So let's look at our x values. 8, 9, 6, 9. We have two 9s. Our x values repeat. They are not unique. When we plug in a 9, we're getting two different values here, right? So same situation as this one here. That's what we do not want. So no, this is not a function. And if it is not a function, there is no need to list the domain and the range. Taking a look at graphical interpretations here. So same question. Is it a function, yes or no? In order to determine if a graph is a function, we use what is called the vertical line test. The vertical line test says if you draw a vertical line anywhere on your graph and it intersects at only one point, then yes, it is a function. If it intersects at more than one point, then no, it is not a function. So taking a look at example C here, if we draw a vertical line anywhere on this graph, it looks like it's hitting one time, right? One time. This is a function here. It only crosses or it only intersects at one point. So yes, it is a function. If we list our domain and our range here, this is assumed to shoot off to the left and to the right on either direction. So remember, the domain is your span of your x values. So you want to look left, you want to look right and see how far out is this graph going. So this one here would be a negative infinity to a positive infinity. For our range, I know this is a little bit hard to see here. This tick mark here is a 1. So it looks like if we're doing our range, we're looking down, up, right? So we don't have a graph. We don't have a graph until this point here. And then our graph shoots up. Do notice that this point here is an open dot. An open dot tells you will have a parentheses. It doesn't actually equal that point, but then our graph is going to shoot up, 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 up. So that actually looks like about a negative 0.5 there. And then it's going to keep going up, 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 positive infinity. So that's what the domain and range would look like for this one. Example D, if we draw a vertical line anywhere on our graph, we're hitting 1, 2 times there. That makes that a no. It is not a function. Example E, draw a vertical line, and it looks like we are just hitting this graph at one point and one point only. So yes, this is a function. Our domain for this function is going to be negative infinity to positive infinity. Again, arrows on either end there. It's going to keep going out and out and out. It's never going to stop. If we look at the range there, and again, I know this is kind of small. It's a little bit hard to see. So if we're looking at the range, again, we're going bottom to top. So our most bottom point here, this looks to be a negative 4. Right? And that is a solid point at negative 4. So we can use a bracket there. Solid points are brackets. Open dots are parentheses. Remember that. Infinities are always parentheses. So it looks like this starts at a negative 4. And again, arrow up top means it's going to keep going up, 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 up. And that is positive infinity. Now, in order to determine if an equation is a function here, so essentially, in a nutshell, for equations, when solved for y, I should have added that little bit into this here. For equations, when solved for y, if you get 2 or more solutions from that equation, no, it is not a function. If you get one solution, then yes, it is. So these are the 2 examples we're going to work with here. So that first part, when solved for y. So if your equations are not solved for y, the first thing we need to do is get them solved for y. So for this first example, all we would need to do is subtract x squared from each side. X squared would cancel on the left. Drop down y is equal to negative x squared plus 4. I'm going to pause there. That's as far as we need to go with this equation here. But I want to get the other one solved for y so that we can compare both of these and figure out, can we determine based off our function if it's going to give us one or more solution, right? One of these is a function, one of us is not. So I want us to take a look at both of them so we can see the difference. If we solve example G for y, we're also going to subtract x squared on either side. Drop down, that y squared is equal to negative x squared plus 4. To get rid of that square, we are going to take the square root of each side to cancel that on the left. And y is equal to, anytime we take a square root, plus or minus the square root of negative x squared plus 4. So that is our function, that is our equation, solve for y for that one. So out of these two options, which one is giving us two or more solutions, which makes it not a function, right? Which one would just give us one solution? All right, so if you're taking a look at this, so the one that is not a function is example G. The fact that we have that plus or minus there, we will have a positive and a negative representation of this here. That gives us two answers, kind of like saying the square root of 9. Well, that's plus or minus 3, right? Positive 3 times positive 3, negative 3 times negative 3. We have two solutions for that, so that is not a function. If we plug in a number here for x, I don't know, let's plug in a 2. All right, if I plug in a 2, well, 2 squared is 4. That gives us negative 4 plus 4, which is a 0. That is one answer and only one answer. So F is yes, this is a function, where this one over here is not. Now, the next thing to talk about here is function notation. So function notation just tells us that y is equal to f of x is equal to y. So maybe previously you've seen examples of equations that look like y equals 2x minus 5. And maybe they ask you to evaluate this and say, well, hey, if x is negative 2, right, evaluate this function when x is negative 2. And that means, you're going to take the negative 2, you're going to plug it into x into your equation, simplify it. Well, function notation allows us to just say this. You have your equation here, f of negative 2 is equal to what? So this is just telling you, hey, plug negative 2 in for x and simplify it. So same meaning, just a slightly different notation here. So we're going to do some evaluating. We're going to pick up some information from our given equation and our given graph. So for example, H, we are given the function f of x is equal to x squared plus 3x plus 5. We are asked to evaluate for these three things right here. First, we are asked to evaluate f of 2. Evaluating f of 2 is telling us to take our equation here, and instead of x, plug in a 2. So this will look like x squared, where x is a 2. So this is our x squared, plus 3 times x, where again, x is 2, plus 5. Simplify this equation here. Well, 2 squared is a 4. 3 times 2 is a 6, plus this 5. And 4 plus 6 plus 5 is a 15. So f of 2 is a 15. Do the same thing for f of x plus 3. So f of x plus 3, same equation. We're going to take x squared, where x is x plus 3, plus 3 times x. Again, x plus 3 goes in there, plus 5. Simplify this. First thing we need to do is square our function x plus 3 times x plus 3. So there's a couple different ways that you can do that. Remember, x plus 3 squared is just x plus 3 times x plus 3. You can distribute that. Distribute your x to get x squared plus 3x. Distribute your 3 to get 3x plus 9. Combine your two middle terms, and you have your you have what you get when you square that. Also, mental math way of doing the same exact thing here. Take whatever in the first spot in your parentheses, square that. X squared is x squared. Multiply the two things together. 3 times x is 3x. Double that, and you get 6x. Square the second thing. 3 times 3 is a 9. So same way to square a binomial there. Distribute the 3 to get 3x plus 9 and drop down that 5. Combine your like terms, so we get x squared. 6x plus 3x gives us a 9x. 9 is 18, plus a 5 there makes that a 23. So f of x plus 3 is x squared plus 9x plus 23. For the last one, we are evaluating a negative x. So we're just going to plug in a negative x here. So x squared, where x is negative x, plus 3 times our negative x, plus 5. Simplify that. Well, negative x squared, negative x times negative x is x squared. We get a minus 3x there plus 5. So that's what we get for f of negative x. It is x squared minus 3x plus 5. For our last example here, we are going to use this given graph here in order to find the following information here. Starting off with f of negative 2. So what they're asking for here, if our x value is negative 2, what is our y value here? So what you need to do is go on your graph and look at negative 2, right, where x is negative 2. So think of it as like imaginary line being there. Where does our graph intersect that imaginary line? Well, right over here. And if we take a look at this point here, this looks like a negative 2, negative 1 is what that point is supposed to be. So at negative 2, our y value is a negative 1. So f of negative 2 is negative 1. F of 5, go over to a positive 5. If we take a look at that, we have a point right over here. The x value is 5. What is the y value? Well, if we look, that is also a 5. F of x is equal to 1. For this instance, they're giving us the y value, and they're saying when our y value is 1, what is our x value? So this time we're going to use our y-axis here, and we're going to go to a positive 1 on our y-axis. Imagine an imaginary line at positive 1. Where does our graph hit? Where our graph hits at this point to this point right over here. So what are the x values for that? So for this strip here, it's all a 1. So it looks like it is a 1 from a negative 1 to a 3. Right? From negative 1 to 3, that's when y is equal to a positive 1. So that would be from negative 1 to a positive 3. Our domain for this function, remember domain, scan left to right. So our leftmost point on our graph is this negative 5. That is a solid point at negative 5. And our rightmost point, we have this arrow. It is going off to positive infinity. Our range is down, up. So starting down, our lowest point here is a negative 2. Our highest point, well, that's shooting off, so that is also going to be a positive infinity.